The next definition was the bane of my existence in grad school. Oh, really? That doesn't sound good. Well, first of all, we need some notation. Let F be a field, and let A1 through AN be elements of some extension E of F. So we'll start to draw a picture here. F is the smaller field. E is the bigger field, the extension field. These A's are all in E. That doesn't exclude some of them possibly being in F. That's not the more interesting case. The more interesting case is when they're not in F. But it's possible some of these A's do happen to be in F. Again, it's just more interesting when they're not. That's the initial context, the initial setup of what they're talking about here. We use this notation, F of A1 through AN, which looks like function notation, but it's not, to denote the smallest subfield of E that contains all of F, and it also contains all the A's. This thing, which looks like function notation, but it's not, represents a field, the smallest subfield of E that contains F and all the A's. Where is this thing in this picture? Who knows? But it contains F and it contains all the E's. Maybe it's here. Maybe that is F of A1, A2 through AN. Could be, if all the A's were in F, then this thing would actually still be F itself. It's possible it could be E itself. But in general, it's somewhere in between. Now, the first place that I got confused in thinking about this concept was thinking that, oh, this thing, this symbol, I guess, represents F and then just add in the A's. That's wrong. It's not just F, then add in the A's. It contains many more elements besides, many more elements in E that are not in F besides the A's. For example, if it includes A1, it includes A1 squared, and A1 cubed, and A1 inverse. Even if A1 squared, A1 cubed, A1 inverse, etc., are not one of the other A's. Why? Because it is by definition a field. It's closed under multiplication. It also would contain, for example, A1 plus A2. 5A1 plus 3A2 squared. Okay. Plenty of other elements that it contains. You could probably say in general, infinitely many other elements. So that's the first mistake that I sometimes made in thinking about this concept. Does this thing have a name, this thing? Yeah, it's effectively called F adjoin A1 through AN, which, and maybe that name is part of the confusion. Adjoin kind of means, seems to mean just add in those elements, but no, you add in many more. This thing, describing it as the smallest subfield of E containing all these things, is the best way to describe it. Initially, at least. We would like another way to describe it, perhaps, but we're not going to get there quite yet. We'll leave it as an exercise to show this is the intersection of all subfields of E that contain F and the set of all the A's. In other words, if K is any field that contains F and all the A's, then K contains this F adjoin the A1 through ANs. Okay, here's the definition that was the bane of my existence. Splitting field. Let E be an extension field of F. So again, you could look at this picture. The picture helps, but it only kind of helps a little bit. Okay. Picture's not the end all be all. It just kind of helps orient you to realizing, oh yeah, E is bigger than F. Let little f of x be a polynomial with coefficients in the smaller field. You could imagine examples in your mind as you read this. You could imagine f is the real numbers and e is the complex numbers. Or you could imagine f as being the rational numbers and e as being the real numbers, or the complex numbers for that matter. Degree at least 1, meaning it's not constant. We say f of x splits in e. Splits in e. That part's not too hard. If you can completely factor f of x. If there are elements little a in f and little a1 through an in e and possibly not in f, in which you can completely factor the little f of x as a product of linear polynomials. And then we call E a splitting field for f of x over f, if in fact E is the smallest subfield of a bigger field that's not specified, in which f of x splits, can be completely factored as a product of linear polynomials, and possibly a leading coefficient that's not 1. Though it could be 1. Took me a long time to get my mind around this thing. And I still, to tell you the truth, wrestle with it. For complicated examples at least, but there's relatively simple examples we can work at understanding. Start with an example here. Okay, let's think about that example without looking at what the book says there. I mean, you're already looking at it, but let me cover it. We are talking about the polynomial f of x equals x squared plus 1 again. F of x equals x squared plus 1. With this example, I don't know if you noticed, there were no finite fields. We're thinking of this. We could think of it as an element of zx. Its coefficients are certainly integers, though z is not a field, so zx is not a principal ideal domain, and it's not, you know, the division algorithm doesn't apply to it. So we prefer using field coefficients like q. All right. We do know, you don't have to prove from scratch, that you can factor x squared plus 1 as x minus I times x plus I, where I is the imaginary unit. I squared equals -1. So that is a factorization. You could say, so f of x splits in the complex numbers, C. Yes, and C is a field extension of Q. Q is a subset of C. It's also a subset of R. And Q, R, and C are all fields, so you could also say Q is a subfield of R. Q is also a subfield of C. And yes, you can say, because we know this factorization holds, that f of x does split over the complex numbers. But is the complex numbers a splitting field for x squared plus 1 over the rationals? No, because it's not the smallest field extension of Q in which f of x splits. Well, that begs a question. What is the smallest field extension of Q in which you can factor f of x like this? It's this thing. Q adjoin I. This is the adjoin notation, which does happen to equal, it turns out, Q adjoin I and negative I, for emphasis, does happen to equal that. Is that obvious? This is the small, you could call Q of I the smallest subfield of C, containing all the rationals and the complex number, the imaginary unit I. You could describe this as the smallest subfield of C, complex numbers, containing all the rationals and also containing I and negative I. Certainly this, the one up top, is a subfield of that subset. Does it go the other way around? Is this thing a subset of that? If this thing contains, listen carefully, if this thing here that I'm pointing at contains negative I, then that'll be true. Why? Because this is the smallest subfield of C containing all the rationals, I and negative I. So if this one contains negative I, then that's smallest one's got to be a subset of that. Does this contain negative I? Yes, because it contains I and it's a field. So it contains negative I. What I just said there the last minute? Very subtle, but very important. I'll say it again. Effectively, by definition, this is a subset of that. The top one's a subset of the bottom. Because here I'm adjoining I, but here I'm adjoining I and negative I. So yeah, this has got to be a subset of that one. The other inclusion works too. These are equal ultimately. Listen again very carefully. This is the smallest subfield of C containing all the rationals, I and negative I. Therefore, if this field happens to also contain all the rationals, I and negative I, it'll be a bigger field, you might say, than this one, though they ultimately are equal. This has got to be a subset of that one. We already know it contains the rationals and I. Does it contain negative I? Yes, because it's a field and it contains I. So it contains the additive inverse negative I. It's a field by definition. There's nothing to prove to say it's a field because it's a field by definition. What does it equal in another way? Is there a way to write the elements of this? Yeah. As A plus BI, where A and B are not arbitrary real numbers, but arbitrary rational numbers. It is a subfield of C. It's not a subfield of R, the reals, because I is not a real number. It is a field extension of the rationals. It's also not a field extension of the reals, because there's plenty of reals that are not in here, like square root of 2 or pi. Your rational reals are not in here. That is the minimal field extension in which f of x splits. This is a splitting field for f of x over q. Notice I use the indefinite article, a or a. Why not the? The reason is because there are other splitting fields. This is another confusing part about it. Wait a minute, how can there possibly be some other splitting field if this is the smallest subfield of the complex numbers in which f of x splits? How could it not be the splitting field? Because there are other field extensions of the rationals in which f of x splits, is the short answer. That are not the complex numbers, though they might be isomorphic to the complex numbers. Can I think of an example? Yes, I can. Coming back to this kind of example once again today. Take the polynomial ring, Qx, so all polynomials with rational coefficients, and mod by the ideal generated, the principal ideal generated by x squared plus 1, which is irreducible over q, and therefore this ideal is maximal, and therefore this factor ring is a field. What do the elements look like? They look like a plus b, ax plus b plus the ideal, where a and b are rational numbers. This is also a splitting field. For f of x over q. And it's technically a different splitting field. The elements are different. Here, these elements are numbers, complex numbers. Here, these elements are cosets of a factor ring, which is a field. They're different. They're different things. This is pretty obviously a field extension of Q, right? Because you could take B to be 0. This has Q as a subfield, all numbers of the form A plus 0i, where A is rational. Emphasizes that Q is a subfield of this. But this also has Q as a subfield, at least if you think in terms of isomorphism. Take constant polynomial representatives. B plus the ideal, where B is rational and the A is taken to be 0. That's a subfield of this isomorphic to the rationals. Same themes keep coming up over and over again today in slightly different contexts. Does f of x really split in here? If so, how? Can I factor x squared plus 1 as a product of linear factors in here? I'm about to do so, but I'm about to do so in a way that's confusing, but accurate. It splits. Well, okay, if I want to be a little bit more official about it, the 1 here is really the unity coset. Maybe I should make this a big 1. It's not the number 1, it's the unity coset. This factors as x minus, this is confusing as well. This coset times x minus this coset. And I'm using the x's in different ways. Maybe I should use a capital X here. Those x's are different than the other x's. The capital X is just sort of an arbitrary variable, you might say, an indeterminate for a polynomial here. The lowercase x's is more referring to sort of more ordinary polynomials and this particular factor ring. Right, this is like relating to the last example, this is like the alpha and this is like the negative alpha. But there's no modding going on here. We're not modding by 3 like we did in the other example. So I should write that as a negative x and not mod it by 3 and write it as a 2x. It's a different example. We're talking about rational coefficients here. That coset is a root, a 0 of the polynomial x squared plus 1, and so is this coset. I've actually gone beyond the example in the book here. These are both splitting fields for x squared plus 1 over the rationals. They are isomorphic. So up to isomorphism, splitting fields are unique. But in terms of what the actual splitting fields, how are they described, they can be technically different. Though again, we've emphasized in this class that an algebraist, whether a group theorist or a ring theorist or a field theorist, really in the end only cares about things up to isomorphism. So in that sense, they might say it's the splitting field. What else does this example get into? It gets into another example, x squared minus 2 instead of x squared plus 1. That splits in R. How? As x minus square root of 2 times x plus square root of 2. Square root of 2 is real but not rational. But R is not a splitting field. Instead, a splitting field is this. Q adjoin root 2. It would also include negative root 2. It would also include things like 2 times root 2, 3 times root 2. Yeah, look at this description. I think we should emphasize another thing here. On Monday, we talked about vector spaces. Why? Why did we talk about vector spaces? I said it was important. Think about this description of Qi here. Every element of this field extension of Q, which is a splitting field for f of x over Q, is of this form, a plus bi. In other words, it's a linear combination of 1, a times 1, and I. In other words, this will be our final thing to focus on today. Qi is a vector space over Q, the rationals, with basis consisting of 2 elements, 1 and I. So the dimension of Qi over Q, which is commonly written like this, put the Qi to the right here and put the Q as a subscript, is 2, because it's got a basis with 2 elements. What are the vectors in the basis? They're these numbers. The numbers are the vectors. What are the scalars? The scalars are also numbers. They're rationals. The reason this is true is in part because of this description. This description up here, this equation right there, verifies that the set 1, I spans Qi. It doesn't technically verify that it's a linearly independent set, but that is true if a times 1 plus b times I equals the number 0, that where a and b are rational, that's enough to imply a and b must be 0. And so this set is also linearly independent, and therefore it's a basis, and therefore this dimension is 2. That is a useful thing, and it generalizes.